Okay, this problem, we've got two cars as shown in the picture, coasting from left to right. Car A, 75 miles an hour. B is 100 miles an hour. When they're 100 meters apart, car A decides to speed up to overtake car B, and of course, keep going. It will do so at an acceleration of 2 meters per second squared. So first question, how long will it take for the cars to be next to each other? So this is going to speed up and go. Obviously, this is still moving. Somewhere down here, they're going to be close to each other, right across from each other. How long will that take to happen? So here I drew a picture where I put time on the going down between these two pictures. So this top picture is time equals 0, and here's a time equal t when they meet. Here's when they're 100 meters apart. Here when they meet. Okay. The distance is going, of course, from left to right, and the 0 is right on B. Okay, here's our 0 axis for the x. So obviously, car A initially at time t equals 0 is 100 meters behind car B. So it's a negative 100 meters, right, from the origin. And they both, and then they meet over here a distance d away from B. All right, so acceleration is given in meters per second squared. The distance between them is given in meters. So the first thing to do is put everything in one set of units. So I put them all in meters, and time is in second. Length is in meters, time in second. If all your units or if all your parameters have length as in meters and time as in seconds, then all the parameters will fall into place. Acceleration will be meters per second squared, velocity will be meters per second, and distance will be meters. You don't have to carry units around, okay? So what I did is I changed 75 miles an hour to meters per second. There's 1609.34 meters per mile, and I did the same for the 100 miles an hour. Now, we have a set of equations that we would like to use, and these are the kinematic equations for 1D motion, okay? So we've got two cars, so we've got two sets of equations. Let's see what we know about car A first. Car A, we have the knowns are on the left and the unknowns are on the right. We know its initial displacement, negative 100 meters, the initial velocity, 33.53 meters per second, and acceleration is 2 meters per second squared. That should be a 2 here. So let's see if you can fix that now. I'll fix it later. Okay, let's see if I can do it real quick. Oops. All right. So squared right there. For car B, obviously the unknowns are time, the distance, the traveled, basically to get there from here to there, basically, and VA. So this is the X for both, actually, okay? For car B, the knowns are its initial displacement is 0, initial velocity and constant velocity is 44.70, acceleration is 0. What's common between these two? It is time, okay? Time is the same. So for this car to go from this position over here, same time as this car to go from here to there. That's where they meet. So this is the equation that has time and distance in it for car A. This is the equation for B. Obviously for B, car B, I'm calling this equation 1. And I plugged in, x0, VA0, the acceleration in here, and x is the distance d from here to there, x equals d. For B, initial distance and acceleration are 0. So all I have is a very simple equation. So now what do we have two equations with two unknowns and plug one into the other one. Plug this into that. So substitute 2 into 1, and now we'll have one equation in time. When we do this, so I plug in D in here. I have this on the right. I rearrange, and I have a quadratic equation in time. Of course, we could use the quadratic formula. When we do the quadratic formula, you know, this is B, this is C, this is A right in front of here. So 1. I got these two times. Obviously, we'll choose the positive time. And so basically, they meet 17.04 seconds, you know, after they are, you know, when they're 100 meters apart, they meet, or, you know, 17.04 seconds later. Now, we could do this graphically. We can plot this on a calculator or using some software like Wolfram Alpha or whatever. And then we can find the zero right here and give us the same thing, obviously. So we know the time is 17.04 seconds. So now, how far down the highway did car A travel? So here's the picture again. So from the figure, it traveled from here, it's 100 meters to here, and it's D to there. So it's 100 plus D. So 100 plus D equals, well, here's 100. D, I use D from VT, from B, for car B, because this is the same distance that car B traveled in the same amount of time. So when we plug it in there, I plugged in the 44.7, that's the velocity of B, 1704. Again, I don't care units, because everything that has length is in meters, that has time is in seconds. If I'm computing distance, it's going to come out in meters. If I'm computing velocity, it's going to come out meters per second. And if I'm computing acceleration, meters per second squared. So here I got 861.69 meters. Well, just to see how many miles, we divide by 1609.34, because that's 1 meter per mile. Here it is, a little bit over 0.5 miles. At what speed is car A traveling at that moment? Okay. So again, whenever it reaches here, we have to use this equation because that's the easy. We don't have to. We could use the third equation, but that's a more complicated equation. It involves initial velocity, final velocity, acceleration, and displacement. This one is pretty straightforward. We know the time. We know how the acceleration is for A. We know its initial speed. We can compute its final speed. So here it is. VA is VA0 plus AT, plug initial velocity of A, 2 for the acceleration times T. I get 68.33 meters per second. I change that to miles per hour. So I divide 1 meter is 1 over 1609.34 miles. And then 1 second is 1 over 3600. 1 hour, yeah, 1 second is 1 over 3600 hours. And there it is. And I got 152.85 miles per hour. That's pretty fast. Okay, that is it for this problem.